Hello everyone, welcome back to the channel. So today we are talking about binary exponentiation, what it is and why do we need it. Okay, so let's have a look at what the problem really is. Okay, we are trying to calculate a to the power b. For example, 2 to the power 16 or 2 to the power 20 or maybe 5 to the power 51, something like this. Now, how if I ask you in order to calculate 2 to the power 16, how are you going to calculate it? You're just going, or maybe let's say 2 to the power 4, how are you going to calculate it? You're just going to say that the answer is going to be what? 2 into 2 into 2 into 2, isn't it? Similarly, if you want to if you want to calculate a to the power 16, where a can be any number, you're just going to multiply a 16 times, right? And you can very easily do this using a simple for loop or a while loop or any loop that you want. So the number of operations in using this approach, how many number of operations is it going to take you? It's going to take you b number of operations, right? Whatever the power is, those many operations will be required by you in order to calculate what the final answer is going to be. Now, what's the problem over here? The problem is, what if you want to calculate a power which is very large? For example, something on the level of 2 into 2 to the power 10 to the power 15, right? So if you apply this approach over here, then it would be O of 10 to the power 15, right? This was O of 16, but then this would be O of 10 to the power 15. So if you do it linearly, if you do it with a linear time complexity, then this is going to lead to a time limit exceeded. So the question which we are fighting with is, can we do anything? Can we have any approach which is better than linear time complexity? That is something, that is the problem with which we are fighting. Okay, so let's have a look. Let's try to break down the problem and see if there is something possible. Let's say I'm trying to figure out what a to the power 16 is. Okay, now this is the problem which I'm trying to solve. I have no idea what a to the power 16 is, right? So what I'll do is I'll break this problem down into a smaller part, and then I'll say, okay, I don't know how to solve the bigger problem, but let's try breaking down the problem. Let's see if it helps. Okay, so I'll break down a to the power 16 into a to the power 8 square. Why? Because this is a mathematical property, right? Whenever you have a to the power b whole to the power c, what does it become? It becomes a to the power bc. So 8 into 2 would become a to the power 16. So it didn't really solve my problem, but then now I don't have to worry about the bigger problem. I have to worry about a smaller problem, a to the power 8, isn't it? Now I don't know what a to the power 8 is, so I'll say the same thing again. Okay, I'll say the same thing again. I don't know how to solve a to the power 8. Let's try to, break the problem down into further smaller part. Let's say a to the power 4 into 2. I need a to the power 4 whole square in order to figure out what a to the power 8 is. I don't know what a to the power 4 is. How can I calculate that? By a to the power 2 whole square. I don't know what a to the power 2 is. How can I calculate that? By a to the power 1 whole square. Now this is something that I know. A to the power 1 is always a. Whatever a is, to the power 1, it's always that number. So I can return that, isn't it? What is this thing going to return over here? A square. So it's going to be a square, then it's going to become a to the power 4, so on and so forth. This will make much more sense when we are actually talking about a real problem. Okay, so for example, 2 to the power 16 is something which I'm trying to calculate. I'll break it down into 2 to the power 8. Again, I don't know what the value is. I'll try to calculate what 2 to the power 4 is. I don't know what the value is. I'll try to calculate what 2 to the power 2 is. Don't know what the value is. 2 to the power 1 is something that I know, right? It's simply 2. So what is the square of 2? 4. I'm going to return 4 over here, so it's going to be 4 over here, right? 4 square is 16, so it's going to be 16 over here. 16 square is, I think, 256. I'm not really sure, so that would be over here. And 256 square, whatever that number is going to be my ultimate answer. So you see, in order to calculate 2 to the power 16, previously I needed 16 operations. I needed a total of 16 operations, but then using this approach, I just needed 1, 2, 3, and 4 operations in total, right? Now let's think about, what if my problem is a bit different. What if the power is odd? For example, if I'm trying to calculate 2 to the power 17, when I had 2 to the power 16, I could very easily break this 16 down into 2 to the power 8 whole square, right? But I can't do that with 17. So now how to solve this problem? We were trying to solve our old problem and now we have a new one. So if you think about it, this can very simply be written down as 2 to the power 8 whole square into 2, isn't it? So this would become, what is this equals to? This is equals to 2 to the power 6 into 2 to the power 1, which is equals to 2 to the power 17. The rest of the scenario remains literally the very same, isn't it? The chain is going to remain the very same, but just this thing is going to be different, isn't it? So this was basically our intuition behind how we can do something which is better than linear time complexity. You can very clearly see that binary exponentiation has a logarithmic time complexity, isn't it? It is log to the base 2 of b, right? So I chose 16 deliberately because 16 is actually a power of 2. It's 2 to the power 4. And as you can see over here, it takes us at max 4 operations in order to calculate what 2 to the power 16 is, as compared to the 16 operations which it was taking us earlier. Now the thing is, how do we code it up? How do I write the code of this algorithm? So it's very simple. You see, what you have to calculate is a to the power b, right? So I will have a function over here, solve function, and what will I pass inside that solve function? I will pass a and I will pass b. Okay. The first thing which I'm going to say to that function is this: calculate. I don't know about the bigger problem. Calculate what the half is. So if I'm calculating 2 to the power 16, I don't know what 2 to the power 16 is. Let's calculate what 2 to the power 8 is. Okay. So and I'll store it somewhere. So I'll say half is equals to solve. I don't know the bigger problem. Let's figure out what b by 2 is going to be. Say, so this was a. I don't know what this is. Let's try to figure out what a b over 2 is going to be. Say, so for example, if this was 2 to the power 16, let's try to figure out what 2 to the power 8 is going to be. And then I need to multiply this by itself, right? So in the very next line, what am I going to do? I'm going to do half is equal, multiply is equals to half. So that basically I'm squaring it. All right. Now, one very important thing, you see, if a was 2 and b was 17, then doing these two steps wasn't enough. I had to multiply by this 2 extra as well, right? So I will check that over here. If b mod 2 equal 1, what does this mean? It means that b was odd. If b was odd, just do this very simple step. Whatever your half is what right now? It's 2 to the power 8 whole square. Whatever your half is, just multiply it one more time with what a is. Okay, this particular step, right? And then ultimately what you have to do is just return your half. Okay, just return your half. So recursion will take care of the overall problem. You don't have to worry about what the bigger problem is. Recursion will take care of it. So let's actually see it in real time, how it works. Okay, let me just change the directory over here. Okay, so let's say I'm trying to figure out 2 to the power, let's say for now let's take 2 to the power 16. Okay, so my a is going to be equals to 2. That is my base. Int a is equals to 2 and the power is going to be 16, right? Now what did I say? I said I'm just going to print whatever solve a to the power b gives me. Okay, that's it. Now how my solve function is going to look like, it's a one thing which I actually missed over here is the base case. So what's, this is infinite recursion which I have written. What's going to be the base case? The base case is going to be when you reach to the power 1, right? So we'll make sure that we include the base case inside of our original code, right? It's going to be an integer function. It receives int a, receives b. Then what did we say? First of all, we'll have the base case over here just so that I don't forget. We said we are going to calculate what the half is going to be. So solve a and then b divided by 2. Okay, then we said we'll do half is multiply equals half, so that it becomes square, 2 to the power 8 whole square. And then I need to see if b was odd. So if b mod 2 equal 1, what I need to do is I just need to multiply half one more time by the what the original number was, a. In our scenario it was 2, and that's it, just return half. Okay, and the base case is going to be that when if b reaches 1, if the power reaches 1, just return a. All right, so if I run this code, let's see if it passes all the test cases. Not all the test cases, we just have one test case. Let's see if it gives us the correct answer, 2 to the power 16, right? And it does. I think this is the correct 2 to the power 16, but just to make sure, we'll do 2 to the power 4, just to sort of make sure that the answer which we are getting is correct. 4 into 4 should be 16, and it gives us 16, right? I hope the problem which we were trying to solve is now clear to you, and I hope that you now know how binary exponentiation can help us decrease the linear time complexity to a logarithmic time complexity. I hope you found the video helpful, and I'll see you in the next one.